Hello and welcome to this course on the applications and algorithms for calculus and mathematica. My name is Devendra Kapadia and I work here at Wolfram Research as a kernel developer for calculus functions. It is a great pleasure to share my thoughts with you today. Now, before I go and discuss the course topics in detail, I would like to go over the goals of this presentation. So in this talk, I would like to show you some interesting applications of calculus to real-world problems. I've chosen applications which are interesting both from the point of view of mathematics and mathematica. Some of them will be a little advanced, but I'll try and go slow and give you all the background and details which are necessary to appreciate their significance. Now, people often wonder, how does mathematics compute a certain integral, or how does it solve a particular differential equation? And so I would like to provide you some insight into the technology underlying the built-in calculus functions. We'll go a little underneath the surface and look at the implementation, but the main point will be to try and convince you that the way we do things in Mathematica is not very different from the way they do them by hand, except that being a large system, we need to worry about efficiency and other details. Now, the key features of Mathematica graphics are animations and dynamic interactivity, and so I would like to use these animations and interactive graphics for understanding concepts in calculus today. Hopefully, this will make the talk even more lively and enjoyable for you. But my overall objective for today's talk is to show you that not only is calculus very useful, but is also very beautiful. By which I mean that there are only a few simple principles underlying calculus, and the entire subject draws its power from these principles. Indeed, calculus is one of the greatest intellectual achievements of mankind, and this explains its importance in science, education, and other fields. So, my overall objective for the presentation is to convey some of the beauty and utility of calculus as seen through the eyes of Mathematica. Okay, it's now time to take on the first application for today, and that is on how to create a soliton with Mathematica. Now, solitons are rather special kinds of waves. They are slightly different from the usual sine or cosine wave because they can travel for long distances without losing their shape or energy. And there is an interesting piece of history behind these waves. So basically in the year 1834, a young Scottish engineer named John Scott Russell observed one of these waves on the Union Canal in Scotland, and he conducted experiments on the properties of the waves. The story goes that in fact Scott Russell was riding on horseback and he saw the wave, he chased for about half a mile and then lost it. He came back, wrote up his work, and as often happens in such cases, no one really believed in the significance of what he had done. And it was only around 60 years later that in 1895, Korteweg and de Vries derived the equation for water waves such as the one seen by Scott Russell. Now, I'm very happy to report that this so-called KdV equation, that's Korteweg-de Vries equation, can be solved in some sense using dsolve. So, here is the KdV equation. It is a partial differential equation, but even more, it's a nonlinear partial differential equation, so here is a nonlinear term. Now, the fact is that such nonlinear PDEs can seldom be solved in complete generality, so when you give this problem to dsolve to solve, then dsolve complains solution requested to a nonlinear partial differential equation trying to build a special solution. And this special solution depends upon three parameters C1, C2, and C3. But that's good enough for me because what I can do now is I can give special values to C1, C2, and C3. And then what I can do is I can run this animation for the solution, and what you see on your screen is a soliton of the type seen by Scott Russell on that day in 1834. Now, solitons are of course quite important in mathematics and physics, but they're also becoming important in telecommunication because they can be used to transmit signals for a long distance without losing their shape or energy. So it's quite nice that one can see these solitons so easily using the graphics available in Mathematica. And now go on to the second application for today, and that has to do with minimal surfaces. And I'd like to begin with the definition of minimal surface, but even before I do that, I should say a little bit about differential geometry. So differential geometry is the application of concepts from differential calculus to the study of curves, surfaces, and higher dimensional objects. So just as the study of algebra at high school prepares one for coordinate geometry, in the same way the study of calculus at college level prepares one for the study of differential geometry. And because differential geometry is the language in which we understand the universe today, the mastery of calculus at any level is a major milestone in the academic career of a student. Now, an important class of surfaces studied in differential geometry are these minimal surfaces. And the question is, why are they called minimal? Well, the term minimal refers to the fact that they have minimal surface area for given boundary conditions. So you can imagine taking a loop of wire and then you dip it in soap solution, and when you pull it out, what you have is a soap film in the form of a minimal surface. And the fact is that one can actually quite easily check whether a particular surface might be minimal, and what you do to see that is to simply rotate the surface, and if it looks saddle shaped all over, then there's a good chance that it's going to be minimal. Okay, now historically the two most basic examples of minimal surfaces are the helixoid and the catenoid. So the helixoid is a surface based on helix. So here is the surface, it's a helical surface, and it's also minimal. The other well-known example of a minimal surface is the catenoid, which is based on a catenary. So here is the catenoid. Now I said a minute ago that these minimal surfaces are saddle-shaped all over, and you can see it quite clearly over here by simply rotating the surface on its side, and you can see it's saddle-shaped all over. Now the remarkable thing about this pair of minimal surfaces is that you can deform one of them to obtain the other without changing the geometry, and that's what is called an isometric deformation. So when I run this animation over here, what you see is you initially have the helixoid, and then finally after some time it will collapse and give you the catenoid. So let's run the animation over here, and you initially have the helixoid, then it collapses further, and finally what you get is the catenoid. Now two questions at this stage. The first question would be, are there any other examples of minimal surfaces beyond the helixoid and the catenoid? And the second question might be, today's talk is all about calculus, and somehow one thinks of calculus as being about, let's say, calculating integrals or finding derivatives. So what has this topic of minimal surfaces got to do with calculus? And the answer to both these questions can be obtained by looking at what is called the Weierstrass representation. So basically, in the year 1866, the famous German teacher and mathematician Carl Weierstrass gave a method for generating minimal surfaces starting with a pair of functions f and g. So for example, let's take f to be 1 and g to be z. And once we've taken these two functions f and g, then we compute these three simple integrals, which anyone can do if they know a little bit of calculus, and then we clear f and g because we do not require them anymore. And then what we do is I switch to polar coordinates, and then quite quickly what we get is a beautiful minimal surface called Enneper's surface. And of course what you can do is you can rotate the surface and admire its beauty. Now I could really stop the discussion of minimal surfaces over here, but I couldn't rest including the final minimal surface for today, which is the so-called Costa minimal surface. Now this is by far the most popular minimal surface. It's appeared on book covers, stone sculptures, ice sculptures, blog posts, and basically in the year 1984 the mathematician Costa introduced this surface which has no self-intersections. Unfortunately, it is rather difficult to define the surface itself because it requires Weierstrassian elliptic functions, so I won't spend much time on that. But let's just run this plot command for the surface, and if we wait for just a short while, then what we get back is this beautiful Costa minimal surface. Okay, I now go on to the third application of today, and that has to do with what are called the Pendulum equations. Now, the Pendulum equations are surely a part of advanced mathematics. On the other hand, the kind of questions that you might ask when you see the Pendulum equations are the same sort that you would ask when you first studied differential equations. So for example, why is it that some differential equations can be solved in closed form and others cannot be solved in closed form? Or what are the properties of differential equation that make it useful in practice? So does nature have some way of selecting differential equations which govern natural phenomena? And the key notion over here is that of a critical point. So here is a first order nonlinear differential equation, and if you solve it, then the solution has a real problem. You see, suppose a C1 is 5 and x is 5, then the denominator is 0, and as you vary C1, so you go from one solution to the next, you again see the same problem. So this is an example of a differential equation with a movable critical point, because the worst feature over here is that everything happens under a square root sign. So such singularities or bad points are called movable critical points. And it was realized by mathematicians that it is the absence of these movable critical points that makes a differential equation easy to solve and useful in some cases. So around the year 1900, the famous French mathematician Paul Pendulum studied second order ODEs with no movable critical points, the so-called good ones, and he found that they can be divided into two groups. The first group of 44 equations can be solved in some sense, either completely or partially. But the remaining 6 equations require new special functions, and these are called the Pendulum transcendents. And these Pendulum transcendents are usually labeled as Pendulum 1, 2, 3, 4, 5, and 6. Now, the good news is that some Pendulum equations can be solved completely in Mathematica itself. So for example, here is Pendulum equation 3 in his list of 50, which can be solved but desolved using Weierstrass elliptic functions. On the other hand, if you go to one of the transcendents, for example Pendulum 2, then what you find is that it can only be solved in a limited way, so you can find special rational solutions starting from a family of polynomials, which I'll now define. So here is the first polynomial, it's 1, the next one is x, and the remaining ones are defined recursively. So for example, here is the 6th polynomial. And the remarkable fact about these polynomials is that their roots lie on approximate equilateral triangles. So when I run this animation over here, what you see are the roots of the polynomials for different values of n, and you'll find that initially you have actual equilateral triangles, and then as time goes by, the sides of the triangles start to curve up. So let's run the animation over here, and you see initially you have exact equilateral triangles, and then as time goes by, the sides will start to curl up, and you only have approximate equilateral triangles. So starting from these polynomials, you can actually obtain rational solutions of Pendulum 2. Okay, now some time ago I spent a very happy summer studying the Pendulum equations, and I prepared a notebook on these equations which I'll now share with you. So this is a notebook on the Pendulum equations and Mathematica. So here is the great man Paul Pendulum. He was a very remarkable man because apart from doing mathematics, he was also the Prime Minister of France during the First World War. So a talented mathematician and a well-known politician. The notebook goes on to discuss these critical points, and then there is a brief mention of the work of the famous lady mathematician Sonia Kovleskaya, who actually used these ideas to solve the differential equations for a top, and in fact she received a prize from the French Academy of Sciences, and the committee was so happy with her work that they actually greatly increased the prize money to acknowledge its exceptional quality. There are further details over here. This is the animation which I just showed you, and then there are some references to the papers by Penleve and his student Gambier, a book by Ince which is still a good reference for differential equation, a paper by Clarkson which I found quite useful for preparing this notebook, a talk by Stephen Wolfram which actually inspired me to study the Penleve equation in the first place, and a more recent reference by Conte. So I hope you'll find this notebook on the Penleve equations useful for self-study and other purposes. Okay, it's now time to go into the internals of our calculus functions, and let's begin with the evaluation of integrals. So roughly speaking, there are three classes of methods for integration. If you give Mathematica an indefinite integral, then we will usually apply the so-called Risch algorithm. This is one mighty powerful algorithm which can in principle solve a large class of indefinite integrals. On the other hand, if we give Mathematica a definite integral, we might either use the corresponding indefinite integral, or we might use a more advanced technique such as the Mellin transform. And of course, we have lots of special methods for improper integrals, logarithmic integrals, you name it, we have it. Okay, so just to give you a feel for how things go internally, let's take up this rather difficult looking exponential indefinite integral. Now it looks difficult, but then you remind yourself of the three basic tricks of college calculus, and what are they? They are the method of substitution, the method of partial fractions, and finally integration by parts. So what I do is I replace e raised to x by t, I do a substitution, and then I use the apart function to do partial fractions, and then what you see is a much simpler expression than what we began with. So you see, t is e raised to x, so one would expect that the answer for the integral will have an exponential part in terms of polynomial, and then this would probably give you some kind of a logarithmic term in the answer, and those two would give some kind of fractional term probably. And the only troublesome part of the integral will probably be this term with t over x, which involves both e raised to x and x. And believe it or not, this is roughly how the Risch algorithm works. It works by making substitutions and doing partial fractions, etc., to find the different parts of the answer. So when you run the example in Mathematica, then what you see is this is the polynomial part coming from there. That's the logarithmic term coming from there. This is the fractional part coming from those two terms, and this transcendental term came from the troublesome t over x part. So we found the answer looks correct. The question is it actually correct? So at this point I'll give you some really good advice for Mathematica, and that is, do check your work whenever that's possible. Let's do it over here, and you do get back the original input, so the answer seems fine. Okay, now go on to the internals of dsolve. Now dsolve is a very modern function since it was completely written a few years ago, and in fact many important algorithms in dsolve are written using the Mathematica programming language. So dsolve code looks somewhat similar to code that you might write yourself, except that there are many more sophisticated algorithms as part of the built-in functionality. The design of dsolve is modular with separate functions for solving each subproblem. So when you give dsolve a problem to solve, then it quickly breaks up the problem into simpler parts, and then each part is solved using a different subfunction. So that's really how a good student would work to solve a problem in mathematics. And because the design is so nice and modular, we can actually automatically select the best algorithm for each problem, and you do not need to give us the method to use. And for me as a developer, the best part about dsolve is that it's really easy to add new algorithms whenever they become available. So typically I might spend 4 or 5 weeks working on an algorithm for dsolve, and then it just takes me a few minutes to hook up the algorithm dsolve, because the whole implementation is so nice and modular. Okay, so as an example for how DSolve works, here is a second order differential equation with right hand side x square, and if you give it to DSolve to solve, then the solution has two parts. The first part is this general solution, and the second part is the x square minus 2, which comes roughly from the right hand side being x square. So internally we have a symbol called DSolve linear homogeneous with constant coefficients, which actually finds the two components of the general solution, which you see right over here. And then we use these two components of the general solution at the next step, along with the right hand side x square from here, and then we apply the method of variation of parameters to give back the particular solution x square minus 2, which corresponds to the inhomogeneous part of the equation. So as you can see, DSolve works in much the same way as you would do by hand, except like I said that it has many sophisticated algorithms built into it. Okay, so it's now time for me to conclude today's presentation with a brief summary of what we have seen today. So first, I hope you agree that Mathematica provides powerful functions for solving calculus problems of all types, whether it's DSolve or integrate or other functions such as sum or rsolve. You really have a battery of tools which are available to solve calculus problems at almost any level, starting from the most basic to the most advanced. And the fact that one can create these animations and dynamic interactivity in Mathematica so easily should make it really useful for understanding concepts in calculus in a much deeper way. Calculus is really a very geometrical subject, although it also has a fair amount of algebra in it, and to be able to see things geometrically should make it really easy to understand calculus and apply it in practice. Now, I've been using Mathematica for the last 14 years or so, and I've seen things improve, and what I believe that what we have today in terms of a combination of symbolic, graphical and other features of Mathematica makes it an excellent tool not just for calculus or for mathematics, but for a wide range of applications. So I really believe that what you have in Mathematica is a great way to solve problems of all types. So on that note, I'll conclude over here. I thank you very much for listening to this presentation on the application algorithms of calculus, and bye.